This is video number 2 on formulas of the topic reflection of light. Timestamps are given in the description box. You can watch parts of video if you're running short of time. In this video, I will discuss mirror formula and magnification of a spherical mirror. Sign convention for reflection of a spherical mirror. This is a concave mirror. It is silvered on the right side. Object is on the left side, facing the shiny portion of the mirror. X-axis, the origin of the x-axis is the pole of the mirror, and the positive direction of the x-axis will coincide with the direction of the incident light. So this is the positive direction of the x-axis. For y direction, the origin is again the pole, and vertically upward direction is positive. So this is the sign convention for reflection of a spherical mirror. The focal length of a concave mirror is negative. This is a concave mirror. From the shiny side where the object is placed, the mirror looks like a cave. So if you take a parallel beam of light, it will go and hit the mirror. And after reflection, all the light rays will pass through a point in the principal axis. That point is called principal focus. If you take one more ray, again you go on. So all the rays of a parallel beam after reflection will pass through the focus. And the focal length is the distance of this focal point from the pole of the mirror. So this is the focal length, and since on the negative side, the focal length of a concave mirror is negative. For a convex mirror, from the shiny side, it will look like this. So a parallel beam of light parallel to the principal axis. The normal at this point is a line joining this thing to the center. For a spherical surface, the radius, which is the line joining the center of the sphere to the surface, is perpendicular to the tangent plane. So this is the normal. This angle of incidence. So the light will come out like this. So that I equal to R. So similarly, this light will come out like this. So these diverging light rays will not meet, but if it projected backwards, it will appear to start from a point which is called principal focus, and it's a virtual focus. One more ray like this, it will go like this, projected backwards, will come and meet here. So all the light rays will diverge after reflection, but it will appear to start from a point which is the virtual focus. So the focal length here, distance from the pole to this one, is on the right side, so it is positive. The origin of the x-axis and the positive direction of the x-axis will coincide with the direction of the incident light. So the focal length of convex mirror is positive. Just by looking at the sign of the focal length of a spherical mirror, one can say whether it is concave or convex. Mirror formula relates the object distance u, the image distance v, and the focal length of the spherical mirror. U is the object distance with the sign, v is image distance, and f is the focal length, and the relation is 1 by u plus 1 by v equal to 1 by f. This mirror formula. And magnification is how big is the image compared to the object. For example, if the image is double the object, then magnification is 2. And one more information is whether the image is inverted or erect. So that can be conveyed by the sign of the magnification. If the image is doubled, but it's inverted, then the magnification is -2. 2 conveys the information that the image size is twice the object size, and this minus sign conveys the information that the image is inverted. And for a spherical mirror, it is defined as minus v by u. H prime is the height of the object. It's a 1D object, linear object like an arrow, and h is the size of the object. H prime is the size of the image. So how to remember these formulas with the correct sign? The formula is 1 by u plus 1 by u equal to 1 by f, but and magnification is v by u with a minus sign. So how to remember those signs correctly? For concave mirror, in most of the cases, the image is on the left side. Object is always on the left side, but the image for most of the cases is on the left side. So v is negative, and focal length is also negative because on the left side. So the terms of the mirror equations 1 by u, 1 by v, and 1 by f. One way to get the correct sign is the term should be positive for most of the cases. So since it's negative here in most of the cases, I'll put a minus sign to make it positive. Okay. Now these are the terms, so I just have to add them up. I will cancel this minus sign to make it 1 by u plus 1 by v equal to 1 by f. So this is the correct mirror equation with the correct signs. So the terms of the mirror equation are 1 by u, 1 by v, and 1 by f, and this should be positive for most of the cases, and most of the cases all three are negative. So I have to introduce a negative sign, and then I'll cancel the negative sign throughout to get this formula. And for the magnification formula, for most of the cases, the image on the left side, v is negative, and the image is inverted. That means I should get the magnification negative. And since v and u are negative, they will cancel each other and give a positive quantity. So this negative sign is required to get the correct formula. So since for most of the cases, u and v are negative, so this is a positive quantity, and this minus sign conveys the information that the image is inverted. So in a concave mirror, when the object is far away, the image is a point image at a focal point. As you move the object closer to the mirror, the image will move out. The object has come closer beyond C, and the image has moved from the focal point to here, and it's inverted. Now the next the object will move and come to C, and the image will come and to C, and both the object and image will meet at C. And after they meet, the object is moving inside, the image is moving outside. So you can see the relation that as the object is moving towards the mirror, image is coming out. So there is some sort of inverse relation between the object distance and the image distance. Still further moving, it's coming out. After that, when it reaches the focus, you get a parallel beam of light. And once it crosses the focus, you get a divergent rays. So that gives a virtual image on the right side. So the first 4 cases you can analyze in one way. So the object is moving from infinity to the focal point, which comes from the first 4 cases, where the image is on the left side and it's inverted. So this is the condition. U is less than 0, V is less than 0, F is less than 0. Mirror equation is 1 by U plus 1 by V equal to 1 by F. Since this is negative, I introduce a minus sign throughout. So that will give me this formula. The quantities in the bracket are positive quantities. It's easy to understand in terms of positive quantities. For a given mirror, the focal is fixed, so right side is a constant. So the object moves, this thing will change, corresponding this has to change. So the sum of 2 terms is a constant. Since sum of 2 terms is a constant, the first term is increasing, the second term has to decrease. So there is an inverse relationship between the object distance and the image distance. So when the object distance is decreasing, as the object is moving towards the mirror, the image is moving away. That's what we saw in the first 4 cases. The first 4 cases, the object is moving from infinity to nearby. The image is moving from the focal point outside. Still further movement inside. They both meet at C. And after meeting at C and the object is moving between C and F, the image is moving out to A prime. So after the focal point, the image is formed on the right side and it's a virtual image. So V has become positive. The mirror equation 1 by U plus 1 by U equal to 1 by F. Since U is negative, I increase the negative sign, put a minus sign. So this thing becomes 1 by U. Similarly for the focal, it is negative. Put a minus sign and put a minus sign here. These are positive quantities. So rewrite like this. So here, term 1 minus term 2 is a constant. Focal length is constant, fixed for a given mirror. So difference of two terms constant means one of them increases, the other one should also increase, or one of them decreases, the other one should decrease. So the object distance decreases, the image distance will also decrease. So for a virtual image, as you get closer to the mirror, if you move from here to here, the image will move from here to here. So there is a direct relation between the object movement and the image movement. For the first 4 cases, it's opposite. It's an inverse relation. As the object is moving in, the image will move further away. Once it forms a virtual image, it's a direct relation. As the object moves inside, the image will also move inside. For a convex mirror, object at infinity produces parallel beam of rays. After hitting the mirror, diverge. But this divergent rays are projected backwards to appear to start from a point, which is the focus. It's a virtual focus. After that, as you bring the object to a finite distance, wherever it is placed, the nature of the image is same. So within a finite distance, you get divergent rays projected backwards will appear to start from here. So this is a virtual image, A prime, B prime. So here the image is always on the right side. So V is positive for all the image object positions. So wherever the object is placed between minus 20 to 0, that's on the left side, V is always positive. It's a virtual image. Mirror formula 1 by U plus 1 by U equal to 1 by F. Since U is negative, I put minus here. And this is a positive quantity. Focal length for a convex mirror is positive because the virtual focus on the right side, so the focal length is positive. So just 1 by F. So here again, the difference of two terms is a constant. So there is a direct relationship between the object and the image distance. So the object moves nearby, the image also move nearby. So here also, when the object moves from here to here, the image will move from here to here. This is also true for a plane mirror, which we use in our everyday life. So if you stay far away from the mirror, the image will be far away. As you move closer, the image will also move closer. So virtual image has the property that the object movement towards the mirror will match with the image movement towards the mirror. Magnification is how big the image is, that's size of the image h prime by h. And that's equal to minus V by U for a mirror. It's a ratio of two numbers. So it can be any real number and it can be positive or negative. If h prime is inverted, this is the object, and if h prime is like this, then h prime is negative, because for y-axis, this is the 0 pole of the mirror and upward direction is positive. So h is positive and h prime is negative if it is inverted image and it's a real image. If it's an erect image, it will be a virtual image. Here h prime is positive. So for this real image, this thing will come out to be negative. So magnification negative conveys the information that the image is inverted. So magnification can take any value on this number line, 0, 1, plus infinity, minus 1, minus infinity. Magnification being a fraction means the image size h prime is less than h. It's a diminished image. Magnification being positive means it's a erect image. And negative means inverted. And whenever the image is inverted, it's a real image. Erect image is a virtual image. Whenever the image is virtual, it is erect. So these are different combinations. So you can say from 0 to 1, it's a diminished image, virtual and erect. 1 and infinity, it's an enlarged image, virtual and erect. Between 0 and -1, diminished image, inverted and real. And between -1 and -infinity, enlarged image, inverted and real.